So you know, maybe you know these these articles in the AMS notices, the what is articles. So I think the title of my talk is going to be what is a homotopy random variable, or more correctly, a collection of homotopy random variables. So the talk is going to be about something called homotopy probability theory, which is a theory in which the vector space of random variables is replaced by a chain complex of random variables. I should mention some collaborators. There's an article called Homotopy Probability Theory. So for references and collaborators, there's an article called Homotopy Probability Theory on a Riemannian manifold, and I think it's in the Euler equation about fluid flow, and this is with Gabriel Drummond Cole and myself. And I should also mention earlier articles on homotopy probability theory with Drummond Cole, myself, and also Jae-Suk Park. Okay, so let me well, maybe I'll use the big board in the middle. So let me say what I think of as ordinary probability theory first. So ordinary probability theory. So you might think of ordinary probability theory as starting with some kind of a measure space or a sigma algebra and some kind of a measure. I want to go a little past that point and say ordinary probability theory is concerned with a vector space V of random variables which might be measurable functions in a measure space and an expectation map, which is a map from V to some ground field, the real numbers or the complex numbers. And so this is what I want to think about as ordinary probability theory. Now, there's a little bit more information here. The space of random variables isn't just a vector space, but is also an algebra. If you multiply measurable functions, you get measurable functions. And so there's a product structure on V. So if you're thinking of, if you're an algebraist, then you think V is an algebra. It's a vector space with a product, an associative product. The target, you know, like the real numbers, that's also an algebra. You can multiply real numbers. But this expectation map is not an algebra map. So an expectation map. So let me say V has an associative product V and expectation is not an algebra map. In other words, the expectation of a product of random variables, like x and y, won't be equal to the product of expectations. The integral of f times g is not the integral of f times g, but rather the difference between the failure of expectation to be an algebra map is actually the heart of statistics. So something like this is called covariance. I guess, I don't know. People call it like this, you have covariance. So covariance, for example, is one example of the failure of E to be an algebra map. That covariance isn't zero for everything, and it's some kind of important measure of correlation between these random variables. Okay. So that's how I think about ordinary probability theory. Now, so I don't know if I make some kind of a mind map over here of, like I have ordinary probability theory. It concerns vector spaces, of random variables, and at its center place, at the centerpiece of the theory, you have a non-structure preserving map. Now, in some sense, I want to talk a little bit about how, I'm not going to really say much about entropy, but it's a little bit like the last question after the last talk, which is if you tell topologists or people in other branches of mathematics like algebra about entropy, what can they do with the information? So in this other areas, you have something which I'll just call derived mathematics. So you have some category you're interested in, you have some notion of weak equivalence. If you want to, you can think of this as a place where you have chain complexes instead of vector spaces. So instead of one vector space, you have a sequence of vector spaces, and you call that's a graded vector space, and then you have a chain map between the graded components that squares to zero. So that's what a chain complex is. But you really here, you only really work with structure preserving maps. So if you have, I mean, there's a caveat here for people that know a lot about, say, operads, for example. In the category of chain complexes, you typically, instead of talking about associative algebras, you talk about associative algebras up to homotopy. So when I say structure preserving maps, I still mean structure preserving up to homotopy, perhaps. So, but still, you don't just talk about arbitrary maps between algebraic objects or arbitrary maps between topological spaces. You talk about continuous ones or something like that. And so homotopy probability theory is some effort here to bridge these two worlds. So that is, take in derived mathematics where you have these really powerful homotopy theoretic tools but they sort of don't exist unless you have chain complexes. Sort of bring them over and see what they can say about ordinary probability theory, but also take this body of experience and knowledge about understanding statistics when you have this non-structure preserving map to a situation in derived mathematics where you might have, you're working in a category with chain complexes but you have some map that doesn't preserve some structure. Oh wait, I'm not supposed to lift these, right? I'm supposed to use this. Oh. Cool. Okay, so I guess maybe I'll say something about homotopy probability theory. Is concerned with a chain complex instead of a vector space. I have a chain complex, so V is a collection of vector spaces and D is a differential, some square zero operator, and an expectation which will be a map from this chain complex to the ground field. The ground field you can view as a chain complex where you just view it as concentrated in degree 0 with 0 differential. And then you have some other structure here. V has an associative product. E is not an algebra map. And let me emphasize a point, is that D is not required to be a derivation of the product in V. If you know something about differential graded algebras, a differential graded algebra is a chain complex together with an associative product, and there's a compatibility between the differential and the product. It satisfies the chain rule. Here, I'm going to assume that there is no compatibility between the product.
Are you assuming a compatibility between E and D?
I'm assuming that there's a compatibility between E and D, so maybe I'll try to suggest that by writing this. So if I think of the ground field, I mean, you could take values in other chain complexes if you wanted to as well. But if I think of the ground field as a chain complex with 0 differential, then I want E to be a linear map. It should respect the vector space structure, and it should be a chain map, so that in that case, it really means that the image of this differential is in the kernel of the expectation. Yeah, so if you wanted to make so maybe the definition of a homotopy probability space would be a chain complex. In fact, I said maybe. Let me give the definition of a homotopy probability space. Would be a chain complex over a field, an expectation, which is a map to the ground field, like a pointed chain complex. And V will also have an associative product. And that's the only assumption made. So that's what a homotopy probability space is, and we had a lot of discussion about categories. So what would the category of homotopy probability spaces be? It would just be the category of chain complexes, pointed chain complexes, with an associative product, and a morphism between two such would just be a chain map. There'd be no compatibility in the morphisms with the associative product. I mean, a chain map that respects the expectation. Okay, so let me put one thing. So I'm going to give an example couple of examples. But let me put one piece of motivation. Why would I pursue sort of these ideas? And I think the motivation here is the motivation is really coming from quantum field theory. So in quantum field theory, you have some functions of fields that are observables. I'll denote them by O. And you associate to O some number given by this Feynman path integral. You integrate over some space of paths. Well, I guess you put O in here. You have an action. And this is some, well, actually, this would be valued in a power series in H bar. So you have some way to, you have a bunch of observables. The observables form an algebra. This is a kind of probability theory. And then you have these correlations. I guess you'd call this correlations. Correlation functions, which are just defined to be the integral of the product of the O's times this expectation. Anyway, quantum field theory has been great and very successful for a lot of things. But if I imagine, thinking back again to an earlier talk, if I imagine some phylogenetic tree of mathematics where here's probability theory, quantum field theory diverged at some point from probability theory. And there are important reasons for that, which is that this integral over this path space isn't really well defined. They don't really have analysis available. And so in order to compute these things, they developed other kinds of tools that you don't see in probability theory. So, and one important kind of tool is they introduce, into the space of observables, they introduce a differential. So you have a chain complex of differential. I mean, you have a chain complex of observables. And then you can do some kind of homological computations in homology and cohomology to produce these correlation functions. And so, so what I would like to do is talk about an approach to package up those tools and techniques that have nothing to do with analysis, but have something to do with homotopy algebra that you see being successful in quantum field theory, and package them up for use outside where you don't necessarily have quantum field theory, but you may be able to organize symmetries using a differential. So like the BV approach to quantum field theory, BV quantization, a la Kevin Costello and Owen Gwilliam, is very much about how you put in a BV differential, in case some of you are familiar with that. Okay. When did I start? Do you know? Quarter to? It doesn't matter? Okay. I mean, a what is talk is, the what is articles are something like 1 page long. So I'm not going to talk for too long. We can catch up. All right, so what's the example that I want to talk about? Let me bring a large board down for this. I thought I could do it simultaneously, bring one down and put one up, but Okay. I mean, it's really nice to have all this space. Okay, enough of that. So let's talk about an example, which is let's let X be a finite volume Riemannian manifold. So what is ordinary probability theory on a finite volume Riemannian manifold? In fact, let's just assume X is compact and connected. Well, your vector space of random variables here are something like the measurable functions. Functions on X. And the expectation of a function on X is given by the integral over the manifold of f times some volume form. dv is a volume form. This is sort of the diffeogeometric approach. And so what I would like to emphasize here is that E, and for simplicity, let me make this smooth functions on X, which I'll denote by omega 0. I'm going to do some differentiation. So, okay, so this is basically the data of the ordinary probability theory on a finite volume Riemannian manifold. Now, if you think about the expectation map, let's just work over the reals. This is a map from an infinite dimensional vector space to a one-dimensional vector space. You really understand this map very well if you understand the co-kernel and you understand some complement to the co-kernel. I mean, it's got a one-dimensional co-kernel. So if you understand the kernel of this map, all the functions that have expectation 0, and then you understand how some complement to that, some one-dimensional complement, then you really understand everything about this map. So let me say first I noticed that the expectation factors through the n forms, if X is n-dimensional, which says I'll call this map star. F here goes to F times the volume form, and then we have a map here which is integration. So this goes to the integral of f dv. Okay, so I'd like to know which functions have 0 expectation value. Yeah. Let's assume it's compact and connected and as nice as we want. Just because the purpose of this talk really is to talk about something structural or algebraic, and there will be concerns about analysis concerns, but I'm just suppressing those. Okay, so here's the picture that. So here's something I want to say. So by Stokes theorem, Stokes theorem implies that the integral So if, let me put it this way, if this function times the volume form is equal to the de Rham differential applied to some n-1 form, then the integral of f dv will be equal to 0. So the integral of an exact form is 0 over a closed manifold without boundary. And did I write it wrong? Or I did? I mean, did it? Is it okay? Okay. So this is Stokes' theorem, and in fact, so what this is really saying is that the expectation of f equals 0 if f times the volume form is exact is equal to d omega for some omega. And for a connected compact manifold, this is an if and only if statement. So this is what you get from Stokes' theorem. Okay, now let's put this together in a nicer way. Okay, so I have omega 0 of x mapping into omega n of x. In fact, this is an isomorphism. You can go both ways. You can take an n form and get back to it'll be a function. So this goes this way, and then you have integration, and this composition here is the expectation, and then I have the n-1 forms here, and I have the de Rham differential. And this star was, I mean, that notation for star was suggestive. This is the Hodge star map. And extends to the entire complex of differential forms. So you have star down here, which is an isomorphism. And you can just define a map from 1 forms into 0 forms. I'll call it delta. You can define, sometimes I think it's called the codifferential on differential forms. It maps. It goes down in degree. It takes a 1 form and gives you a 0 form, a 2 form and gives you a 1 form. And it's defined to just be, you take this 1 form, you associate via the star map an n-1 form, then you take the de Rham differential, and then you go back. And so I can summarize the situation by saying a function f is in the kernel of the expectation if and only if f is in the image of this codifferential. And I can summarize this in another tidy way by saying just want to lift it up a little bit. So I can sort of, it's like take a small interlude and just recap. So here's a concluding. This is like the conclusion of this example so far. The concluding statement is I can take all the differential forms in the manifold together with the wedge product. So that's a nice graded vector space together with this codifferential. That's a differential on this vector space. And then I can take the expectation down to the real numbers. This is a chain map. And this is a chain map. And this is a homotopy probability space associated to the Riemannian manifold. I might call it the real valued homotopy probability space associated to X. And so let me make one remark. I'm extending E to all differential forms. I'm saying the expectation of a function is as defined, but the expectation of a 1 form or a 2 form is just 0. You extend it by 0. And the concluding statement is this expectation map is an isomorphism in cohomology. So that you know.
On the top manifold is contracted. Only top cohomology. It's only on the top.
How do you find E on lower degree forms?
No.
0.
Yeah, but then
Yes, it's not true. Because you could have cohomology in any dimension. Yeah, you're supposed to connect that. If the manifold is connected, it's true that
Is an isomorphism in H.
Yes.
H0, I guess. Right. What's that? Yeah. What were you going to say, Tom?
I thought you just wanted it to be the center map cohomologies. No, it's okay. No.
Yeah. So it's true. I could replace this space here with the cohomology of the manifold and then sort of extend. Okay. Okay, so that's a concluding statement. Now, I think it kind of exposes an attitude about homotopy probability theory. If you know something about homological algebra, you have some module and you've got relations and you want to study it. You replace the module by something without relations, like a free module, but you put in a differential that resolves the relations. Here's a similar idea. You have some probability theory, but you've got all these relations among expectation values. You'd like to replace that probability theory by the random variables by a chain complex of random variables, so that and then encode the relations somehow in a differential. I think there's a nice example here. I'm trying to decide whether I should give an explicit example. So in explicit examples, what this allows you to do is to compute a bunch of expectation values without doing any calculus, but by doing some, or not doing any analysis or computing any integrals, but just do some computations in homology. Okay, now here's a very important point, which is that this codifferential here is not a derivation of the product. So this, the codifferential here maps differential forms to differential forms of 1 degree less, but it's not an algebra map. The de Rham differential is famously an algebra map. It's a derivation. It satisfies the chain rule. But once I've transported by star, because star is not an algebra map, this codifferential is not an algebra map. So this is not, is not a derivation. So you don't have a product rule. Okay. All right, so let me try and wind try to finish up and say, what is a collection of homotopy random variables? See, if we were only concerned with expectations, this would everything would be over. You look at a chain complex, and you have this expectation, which is a chain map, and then that's the end of the story. But the real point is to understand the statistics. So how do you really get meaningful homotopy invariant statistics out of this situation? That's and that's sort of the challenge. And let me try to illustrate a little bit of the challenge. So a first approximation to the definition of a homotopy random variable. So X is an element of a chain complex, meaning an element of V, should satisfy is a homotopy random variable if and only if d of x is 0. So you really only expect to get meaningful numbers from expectations on closed things. And you can imagine an analogy to homological algebra. If you take your module and you have relations, you've got a lot of choices about how to resolve those relations. And not everything about those choices will be invariant of the underlying module that you're interested in. So here, if you want theorems to be true, like homotopic expectation maps give identical statistics, or if you resolve an ordinary probability space as a homotopy probability space in two different ways to get meaningful numbers out of the homotopy, the extended space that are truly related to the underlying space, you want something like this to be true. This is true in quantum field theory. You typically only define the path integral for observables if the observables are closed under the BV operator. Okay, but the problem with this is that the differential doesn't respect the structure. So even if x is closed, and y is closed, this does not imply that the product will be closed. Because the way you normally prove that you get a ring structure in homology for a manifold is you have to use the product rule for the differential. D of x times y is dx times y plus x times dy. And so if both of these vanish, the product will have a well-defined cohomology class. But that's not true if D doesn't satisfy the product rule. So what do? Well, you introduce. So this is the first approximation. This is the problem. You might be able to talk about the expectation of x and the expectation of y, but you can't talk about their covariance. What's the solution to the problem? Well, you want to introduce the moment generating function. So introduce a formal parameter s, so I can look at power series in S with coefficients in V, and then I can take something like the exponential of Sx in here. This is what you expect it to be, 1 plus Sx plus s squared over 2, x squared plus x cubed over 3, x cubed, and so on. And then what you'll see is that you extend D as D was a derivation. I mean, D was a differential in V. You can extend it linearly over S, and you can say D of the exponential of Sx equals 0 in this ring, power series in this variable S, if and only if D of x to the n equals 0 for all n. So in other words, you introduce this parameter, and you look at the moment generating function for this random variable. And if that itself is closed, then you know that the random variable x will have meaningful moments for all of its moments will be meaningful. And so this gives rise to the main idea. So you need to introduce parameters. And so you introduce parameters. So for example, if I have a collection xi, where i's come in some set of indices, what I can do is I can form the exponential of si xi in v bracket bracket. I don't know why I'm using lambda. S is some, okay, lambda, some set of indices, and I can form S is just the collection of some formal parameters. I guess this is what I have to do. And so you could, and then what you can say is that this will be closed.
You put a sum?
Yeah. Put a sum. So this will be closed if and only if all the joint moments among the xi are sort of meaningful, meaning that they're closed. Now, I'm still one step away from giving the definition, because a lot of times you might only be interested. Suppose you have an x and you're interested in it. You care about its expectation, maybe its second moment, maybe its third moment, but you don't care about the fourth and so on. You might want to just say, work in power series in S modulo S to the fourth. You might want to do something like this. And allow your parameter rings to be quotients of power series rings. Quotients are not very well defined homotopically for various reasons, like you might know if you have a group acting on a manifold, that's not a very, the quotient of the group by the manifold is not a very good object homotopy theoretically, and instead you do this Borel construction where you take EG for the group G and you cross over G. It's, so you do something else homotopy theoretically. So the way you handle quotients of rings homotopy theoretically is you just work with power series rings that may have differentials in them. And so, so I guess the definition, maybe I'll give myself a little more space. So this allows me to say the definition of a homotopy, collection of homotopy random variables. So suppose V with D, V has some product, and then you have an expectation, is a homotopy probability space. and R is a power series ring over whatever my ground field is. Let me write it this way. R is a power series ring in some variables together with a differential is a differential parameter ring. Then a collection of homotopy random variables parametrized by this parameter ring R is an element curly X in V tensor R, satisfying D of the exponential of the collection equals 0. So that's what a collection of homotopy random variables parametrized by a ring is. And then you can go further, the homotopy statistics of this collection is defined to be the expectation of this moment generating function, which is an element of this ring, but you want to think of this ring as having parameters, and the coefficients of those parameters are exactly things like joint moments of the elements in this collection. So I think I'll stop here, but let me say, without pulling another board down and writing more, just saying the fundamental theorem of homotopy probability theory, if you are wondering, is that there's a notion of homotopy between homotopy random variables. What you want to do is to introduce another parameter, t and dt, so you tensor with the differential forms on the interval, or the one simplex. And then you have a new parameter t, and you ask, and then if you have a collection that's in this larger parameter space, that when you set t equals 0, you get one homotopy random variable. When you set t equals 1, you get the other. Then you would call the two elements x0 and x1 homotopic. And the theorem is that homotopic collections have the same statistics. And so this allows you to do a bunch of cool things and do a lot of computations using homotopy algebra to actually compute things that you cared about with completely new methods. So, are there any questions? Yeah.
Is there anything interesting to say about independence of homotopy random variables?
Yes. So one way to characterize independence is by saying something like a collection will be independent if and only if some particular combination of the moments, called the cumulants, vanish. And so the way I've written it here, the way I've organized these statistics here are as the expectation of this exponential. So you want to think of these as like the moment generating function. But there's a variation of this construction that would give you the cumulant the cumulant generating function. And so saying that that is 0, or if you have a differential in your parameter ring is exact, would be the definition of independent. And you could do this for classical independence, or what's called Boolean independence. And there should be some comparable notion related to free independence. Now, since you mentioned operads in your last talk, I should say that what I've done here is related to, so if you read this paper about the Euler equation and the Navier-Stokes equation, it's presented this way. But in the earlier papers, it was all presented in the language of various operatic constructions and much more abstractly and categorically. So this is sort of the Lie infinity version. And if you wanted to do something for free probability or Boolean independence, you would choose a different operad. I don't know.